Hey everybody, Dave Lindbergh in Hong Kong with a special episode of the THD Podcast. This is now year 2. So 12 months we've been clowning around on here trying to talk audio stuff. So today we're going to do a special episode learning about ANC headphone technologies and the difference. I want to know about feedforward, feedback, and hybrid technologies. And we're going to get Simon to explain it for us. But without delay, let's not forget our sponsor, the ALTI, the Audio Loudspeaker Technology International. We encourage everybody watching to check out their website and consider becoming a member in this great kind of networking association for the audio industry. They have an event coming up October 24th, 25th in Orlando. They're going to go live with an in-person trade show. So get out from under your COVID rocks and go check out that event. So, coming in, as always, is Simon Weston from Japan. And Simon, people might not know this. They might have just been watching all the other stuff we talk about. But Simon is an expert in ANC headphones. At least I tell people he is. And so how are you doing today, Simon?
Pretty good, mate. Pretty good. I know enough to fake it anyway. So we'll see how we go.
Okay. So I guess noise cancellation in general, I mean, we can broaden the topic. We can talk about like Peltor or earmuffs that construction workers use. That is kind of one form of passive noise cancellation. And so that's kind of the origins of the technology, I guess. And then this active noise cancellation concept of putting out wavelengths or sending cancellation waves to stop people from hearing these noises at different frequencies. So we're going to find out how that works.
So it's probably worth just quickly covering that because you mentioned it, passive versus active, and what is the difference. And so it's a pretty simple idea. The passive noise cancellation essentially means you're blocking the sound from getting to your ear or whatever the destination is. So the technique is to make a headphone, let's say, an ear shell. And here's your ear in here, with the ear canal, and you're listening on the diaphragm in here. So the sound waves are coming in. Essentially, you're trying to reflect as much as you can off that hard surface. And some sound will still get inside. And what you're trying to do then is have like a large cavity inside so that sound energy disperses inside the chamber. And thereby you reduce the amount of outside noise that's getting to the ear. So that's just a passive cancellation. You're trying to reflect sound as much as possible, and whatever sound does get in, you're trying to dissipate it essentially inside that ear shell.
Okay, that's part of the technology today, the passive nature of it being an occlusion effect. And I think the history of this was that, what's his name? Dr. Amar Bose was on a flight in 1978 from Zurich to the States. And he didn't like hearing all the airplane noise in these little headphones. I'm not sure. He was probably in first class by that point in Bose history. I mean, they were 70s. They were kind of just getting started. But he was a professor at MIT, so I don't know how those guys roll. But they're kind of royalty in the engineering world, MIT profs. But anyways, so it started in 1978, but it wasn't until 1989 that Bose actually launched the first. And it was for aviation applications, active noise canceling device. It was apparently far too bulky for consumers. But then in 1999, the Bose company launched their first QC series, or Quiet Comfort, which started to incorporate this active component. So that's kind of an interesting step in history. So this, maybe on this diagram, you could point out how the active component starts to come into play.
So what active noise cancellation means, the principle is it's called the superposition of sound waves. And what happens is you have some sound wave, and we'll draw it like the old sine curve, like that. If you have some sound wave traveling through the air, and you mix it with something that's equal and opposite, the pressure from those two sound waves add together, and you have positive and negative. And adding the positives and negatives, you'd end up with essentially zero pressure.
Right.
So that's the principle. What you're trying to do is have some generator that produces the equal and opposite sound pressure as the wave you're trying to cancel.
Mm-hmm.
So there is actually an interesting point about this, and the question becomes, what happens to that sound energy when you do this cancellation? And just before we go into that, this concept is the same as what you would have for standing waves in a room. You have loudspeakers in a room, people are concerned about the standing waves. It's exactly the same thing. There's some speaker, speaker generating some sound waves, and that flies off, and it hits a wall and bounces back. And at some point on that reflection, it's a bit idealized, of course, because in a room the sound waves bouncing off all the walls. But at some point, those two waves will meet each other at a point where they're equal and opposite. So there'll be a high pressure area and a low pressure area, and you'd get a standing wave. And depending on the frequency, there may be many standing waves. But imagine a sort of a lowish frequency. So that there's just one in this type of a setup, you'd end up with at some point that the sound pressure level, I'll just draw it as a line, let's say, imagine like this. Then here's like a little graph of the sound pressure level. With no wall, you just have this flat line. But when you reflect that sound back and mix it together with the incoming sound, in some places you'll add and in some places you'll subtract. So you'd actually end up with something like this.
Right. So that's why
the waves are equal and opposite, and the apparent sound pressure level is very low. Ideally zero, but it doesn't quite work.
So that's why people are trying to build sweet spots. So like in live sound, a lot of people think 10 rows off the stage is the best location. And of course, it depends if it's in a closed auditorium or whatnot. But if you see people with their hi-fi setups, they'll typically have a carpet on the floor, and then they'll have some kind of like sound insulation on the side walls and the back walls. And that's trying to prevent those waves from coming back. Is that what that's about?
So you can put some materials on the surfaces to try and reduce the energy reflected, and therefore reduce that standing wave problem. It's not very effective at low frequency, because low frequency energy tends to pass through, carpet or materials fairly easily.
Right.
And also you talk about the sweet spot. It's true, but the position of the standing waves just changes with frequency. So when you're choosing a sweet spot, generally you'd be choosing somewhere where the bass level is nice and even. The high frequency stuff gets a bit more mixed up, so you sort of get away with it, I guess.
So that sweet spot for really fanatics, it could vary from one person's ear to the other. Yeah. Or is it kind of really minutia at that point?
Yeah, it's a bit minutia, I think. Yeah.
Yeah. Well, but so are super hi-fi freaks.
Definitely. So people probably know this principle fairly well in terms of active noise cancellation.
Okay. So which one would we talk about one first, or we talk about the concept in general first?
So that's the concept in general, and both feedforward and feedback are trying to apply this principle that if we make an equal and opposite sound wave, we would get a zero result. There'd be no apparent pressure at your ear. I was actually, I've written down F, but just before I do that, I was going to talk about this concept of what happens to that sound energy. So in the case of like a standing wave type of a thing, the waves actually just pass right through each other. There just happens to be a point at which the apparent pressure, the net pressure, is zero, but that wave energy doesn't go anywhere. It carries on and passes through, comes out the other side of this dead zone, let's say, and carries on. Okay. And there's a bit of a debate. I don't know the answer to this one, so maybe people can throw their hat in the comments. But there's one concept that I'll talk about feedback then first, and to highlight this. And then in case of feedback, you have a speaker here inside the ear cup and a microphone. You draw a microphone like that, and that goes through some FB filter.
Feedback filter.
Yep. Okay. And so you have some sound energy inside this chamber, and you create a cancellation signal from the speaker. There's one concept that what you're doing effectively is pulling that energy out by moving the speaker diaphragm, and it's going out as heat into the coil. It's being transformed into electrical and heat energy in the speaker.
Okay.
So it's not just a momentary crossing of waves where they net out to zero. Actually, you're pulling that energy out. Now, I'm not so sure that that's a very good analysis, because the efficiency of speakers is not that high. So yes, you may be able to pull some of that energy out, but it's 100% perfect. So probably not. I think all you're doing is creating a zone where you have a null in sound energy. But, it would pass outside that headphone, and outside of the headphone, you'd be having other things happening, increase in sound level and so on. So it's just a topic I don't actually know the answer very well. But what happens to that sound energy? Possibly that most of it, nothing happens to it. It's just a momentary null in this space and time. And the energy isn't actually going anywhere. Some of it would be converted out as heat and electrical energy in the speaker. So I started off with the feedback diagram here, and in all cases you're talking about some noise coming from the outside world. I'm doing these wave fronts diagram, and it passes through the earphone, in and around the ear pads and whatever. You might have a porting here, in through the porting inside the chamber, and on into your ear canal too, and you hit the eardrum in there. Now what you do, the microphone responds to that, produces an electrical signal which passes through some kind of a filter, and then is a sound wave is put out by the speaker. And
so the same speaker that's producing the audio for your ear is also producing the cancellation waves.
Yep, exactly.
The opposite waves. Okay.
Yep. If we just take this case where there is no audio, and we can add the audio in a minute. So the speaker is trying to generate an opposite waveform to whatever that microphone is picking up. What it means by feedback is that whatever signal that speaker puts out is also picked up by the microphone. So there's actually a loop of the pickup and the speaker. So you have the karaoke microphone screaming problem. That's also a feedback thing where the speakers are outputting a sound that's picked up by your microphone, and it just keeps doubling up and amplifying up as it goes around the loop until it just starts screaming.
If people have a feedback formatted active noise canceling product, when they turn it on, they can hear a bit of a feedback loop ring in some of those, I believe.
Some of them potentially, but what you've done with the filter is you've arranged it so that the signal coming out of the speaker is always opposite phase.
Okay.
To the signal coming from the microphone. So they never add together.
They never
That's your objective. And what you end up doing is reducing the sound always.
Okay.
But of course, in audio, the sound that the speaker produces is not just a perfect representation, or the acoustic signal you get out is not a perfect representation of the electrical signal, because you have the acoustic effects. So there's a frequency response, or there's a difference at different frequencies. And inevitably what happens is, let's say you give the speaker a one signal to output at a very low frequency, say 100 hertz. I'll just do 100 hertz, not that low. And you get more or less exactly the same thing out that you put in. But as you go up in frequency, the distance between the speaker and the microphone starts to become important. So there's, as I say, so like a time delay, let's say, and so and also a change in the magnitude. So 1,000 hertz, the level might be different, and then at 10,000 hertz, different again. I'm just drawing some points. So you end up with this a response where the signal that you're getting out is not the same as you put in. And most importantly, the phase will change. So magnitude and phase are actually the same thing, just looking from a different perspective, essentially.
Okay.
And so then you say, well, I've got this, this filter, and the output from the speaker, the phase has become reversed at some point, or most of the way to reversed. Then you have this whistling problem. We generate a feedback loop. So you have to try and construct your filter so that in this feedback loop, and the frequencies at which the phase is gone past halfway, it's getting close to being in phase, adding the sound waves again, you have to have such a low gain, a negative gain, in fact, so the sound is diminished on each loop, and then you don't have that squealing problem.
Okay. All right. Yeah, I'm trying. I had some Sennheiser. They were on-ear noise canceling probably 10 years ago,
Yeah.
And I noticed that there was this kind of, when you turn them on, there was a thing, and then it would kind of normalize itself.
Okay. Some of them have like a slow turn on mode because you don't want to have a pop when you first hit the power.
Right.
Yeah. So the concept anyway with feedback is what you're trying to do is take a signal from the microphone, pass it through some filter to get an opposite phase signal out of the speaker. However, that signal out of the speaker at some point in the frequency range would reverse because of the acoustics of this system. And therefore, you have to diminish your gain through the filter at those frequencies so it doesn't become unstable or start squealing.
Okay.
So I drew sort of a semi-curve here. You often end up with something like this in a headphone. I'll just draw it a bit more idealized. My frequencies are a bit off. Low frequency is fairly even, and then the level drops down in the mid-range, and maybe you have some bumps and so on at high frequency. And when your magnitude looks like that, your phase has more or less the same characteristic. That is to say, the phase in this point would be a 0. In fact, I'll draw that. It rolls off at low frequency. So the phase would look something, is that in the picture? I'll just move that down a little bit.
Yeah.
The phase would look something like this. And then off she goes.
Okay.
And let's imagine here, or a bit off, but here is like a 0 phase. So everything's perfect at that point. If you just had one frequency, you would need to do nothing with the filter. I mean, if everything was 0 phase, the filter doesn't have to do anything. You just send that signal back out the speaker.
Okay.
But that doesn't happen. The phase starts to go very negative, and let's say you get past halfway, which is 90 degrees, or 180 degrees, which is completely out of phase.
Mm-hmm.
At that point, the signals are going to start adding together again, and the thing will become unstable and squeal. So the whole game with feedback is to construct this filter that prevents that from happening.
Okay.
So in the simple form, you might end up with a filter that does a bump like that. At high frequencies, the gain is way down. At low frequencies, the gain is way down. And at the nice point where everything is, I keep interchanging in phase and out of phase, but when the phase is in the place that you want it, you can have your maximum gain of that signal.
Okay. Makes sense.
So in feedback, there's no limit to the amount of gain you can put onto it, except that you end up, if you keep increasing this gain, at some point you will start having instability.
Okay. So yeah, just in summary, I guess feedback has the mic pickup within the ear cup or within next to the ear canal.
Yeah.
And it runs through a filter to give you the opposite phase frequencies needed to reduce that unwanted noise.
Yep. I'll quickly cover feed forward now, and then we'll come back and contrast what that actually means. So in feed forward, the microphone is outside the ear cup. And I'll do my microphone as a line in a circle, and then the ear cup here, speaker, there's your head, there's your ear canal there. Again, sound comes from the outside, passes through everything, it reaches your ear canal.
Mm-hmm.
This microphone's going to pick up a signal, pass it through some feed forward filter, and put it out of the speaker. So what you want here is that there's that more simple case, or more easy to comprehend, where you just want that to be the opposite waveform. So actually, if I use these, I've actually got colored pencils, so we'll do that. Imagine those are the positive wave fronts of that outside noise. If you get your speaker positive wave fronts to end up exactly halfway.
Yeah, got it.
So this would be a down and an up and a down and an up, you see, and this would be an up and a down and an up and a down. They would cancel each other out.
Right. Okay.
And in the ideal sense, there's no connection. That the sound from the speaker never reaches that feed-forward microphone. So you would never have the stability problem. And then, in feed-forward, then what you do is you say, okay, I've got some sound coming from the outside that's picked up by this microphone. I want to know what that sound wave looks like when it reaches the eardrum.
Okay.
And generally do this in terms of a frequency response or a transfer function. So you come up with some curve, basically, that says what's the sound like that comes from this, whatever you arrived at this microphone, what does it look like when it reaches the eardrum? And it won't be exactly the same because it's passed through a headphone, shell, AirPad, etc. It's traveled down an ear canal and hit the eardrum. So it's not going to be the same waveform that microphone sees. There'll be some difference between it. And it's a waveform, but you can also phrase that in terms of a frequency response or transfer function. That's fine.
Right. So it's basically it uses that pickup and then it runs a little bit of modeling to know what's on the other side. So it's been you've trained it or tested it previous to
so you just
putting those filters.
You just have to measure that directly, actually. Then you do the same thing for the speaker. When I put some sound into the speaker, what do I get out at the eardrum? And again, it's not the perfect correlation between the electrical signal that you put in and what you get at the eardrum, because again, it goes through this acoustic chamber down the ear canal and reaches the eardrum. And so you have the curve is a little bit different. In fact, that is the frequency response of a headphone.
Right. And then back into the minutia kind of argument. So some people could have slightly different efficacy based on how that ANC tuning is done?
Definitely.
Okay.
You get into that level. And then you just have to calculate what should I do with this microphone signal so that when I put it out of the speaker, it ends up as a cancelled sound wave at the eardrum.
Right.
And so there's a direct calculation for that in Feedforward. And then you can work out what the filter is going to do. So when I get a signal from the microphone, what should I put out of the speaker so that the sound wave from the outside reaching the eardrum and the sound wave from the speaker reaching the eardrum are exactly opposite.
Okay.
Now you just said people with different ears and so on, does it make difference? It does at mid and higher frequencies. At low frequency, the sound wave is so long that there's really not much difference between what arrives at the ear for different people's ear canals. But once you get into mid and high frequency, yes, definitely makes a difference. Also makes a big difference where the sound wave is coming from. So you could imagine, just sketch again. Try to do a little bit tidy this time.
Green's a little hard to see.
Green's a bit hard to see. I'll switch to the nice blue then. And then here's your head, and I'll do that whole ear canal thing there. So I just showed the typical one that you draw. It's a bit off to the side. I'll try and scrunch it up. You have this nice sound wave. So you have a sound wave that's coming in nicely just from the outside, and this kind of, you imagine it's like a ray, a straight line traveling through and hits the ear canal. But in the real world, because sound's coming from all directions. So you may have sound coming from some other direction that, temporarily you'd say, it actually reached the eardrum before it reaches that microphone. So how's that going to work?
Like the voices inside my head?
Pretty much. Now, if the frequency is very, very low, so that I'll try and draw like a wave, let's say. Mm-hmm. You can imagine there's a wave form like this. That's not that low. More like a high one. Okay, let's start with the high one then. This wave is reaching here at some time before it's reaching here, and there's a huge difference between what part of the waveform reaches the ear canal and what part of it reaches the microphone. And in that case, you can't really do too much about that because it's just too high a frequency. So there isn't a strong correlation between those two signals. If you had an incredibly low frequency, let me try that with this red, the waveform would look something like this. It's going to be difficult to draw. You can imagine a huge wave.
Right.
So what reaches the ear canal and reaches the microphone is almost exactly the same, because the wave's so long that it's basically the same pressure. So it still works at low frequency, regardless of what direction the sound's coming from.
Yeah, and I think with in general the ANC, like the over ears are probably very superior, because at the high frequencies they could block they can block that high frequency signal from getting into your eardrum with the occlusion effect.
Yep, that's true. Yeah.
Right. And
just
then,
by passive isolation, definitely.
Right, but then now that people want to put these ANC systems into TWS, true wireless stereo or earbud applications, that occlusion is next to impossible.
Well, it's not entirely true. I mean, earbuds with an insert silicon, they can do a good job of blocking sound passively.
Yeah. Okay. Yeah, fair enough.
In that regard, you'd have this problem ultimately then. What's the distance between that microphone and the ear canal? And as that distance gets larger, the high frequency that you can go up to gets lower and lower.
Okay.
So if they're very close together, and you have some waveform, and the two things are this distance apart, one is here while one's here, and the difference in the pressure of that wave at those points is really not much at all. It'll work fine. But if that distance is larger, say on a large headset, and here's this is our microphone point, let's imagine, and then somewhere way over here is the ear canal, then you say, well, this is getting to be quite a big distance between the two, and I can't be sure that regardless of where the waveform's coming from, if I just say, oh, well, we'll just do the magnitude down by this amount at this frequency, that would work for one particular waveform arriving from one particular direction, but from another direction, it may be a totally different relationship between those two levels.
Okay.
So for feedforward, you're trying to do this thing where you're matching a response from microphone to ear canal and driver to ear canal.
Okay.
And in fact, you just calculate a filter directly from that. There's no instability problem because there's no connection between those two. You may add noise rather than subtracting it, but you won't have instability. So you're trying to match this transfer function. I was going to come back to and just say for feedback, you're not trying to match that transfer function. You're trying to produce as much gain on the signal as possible without going unstable.
Okay.
So there's two quite different philosophies, and when people say, "Oh, it's, noise cancellation," it's not. Except for the fact that they are trying to use destructive interference or adding opposite sound waves together, there isn't any other similarities really in terms of the design principle.
Okay, so then if we talk about hybrid, are they taking these two kind of opposite theories and putting them together and trying to get a utopian or best-in-class result? Is that... Exactly.
So actually, hybrid is... I don't really like the term hybrid.
Okay.
I think it should be used for a different reason, but that doesn't matter. You can stitch these two things together completely independently. You can switch them on and off completely independently. So yeah, in hybrid, you just have your microphone on the outside going through a feed-forward filter, and didn't leave myself enough space, but we'll drive that into the speaker. Then a microphone on the inside going through a feedback filter. And you can just sum those two signals together. They don't care about each other and pump them out of the speaker. This part will do its feed-forward job, this part will do its feedback job. If you switch that one off, it wouldn't affect the feed-forward at all.
Are there any brands that have the ability to switch between feed-forward, feedback, and both at the same time?
I don't really know, actually. I know there's plenty of brands where they have ANC level 1 and 2, and I just wonder if that's what they're doing when you just switch on, one only and not the other one.
All right.
So I don't really like the use of hybrid for this because it implies something slightly different in my mind. This is just putting two parts together. If you say you have a headphone with Bluetooth and a cable input, do you call that a hybrid headphone? I don't know.
I think it might be a spillover from automotive with like the Toyota Prius that has the gas and electric. They call those hybrids. So.
Yeah, fair enough too. So the key points here, you have these two filters for feed forward and feedback, and we'll just delve into that a little bit too. And the original Bose one uses a circuit it's a feedback only. They started with feedback only. In some ways, feedback is a little bit easier. Like the theory of this instability is a bit more difficult to begin with, but you don't have to perfectly match some filter function of this microphone to eardrum and speaker to eardrum. You just have to produce something that reduces the high frequency so that you don't have instability, basically, and the low frequency too. Slightly more difficult conceptually, but implementation wise, it's a little simpler, I think.
Okay.
So they did feedback only, and you have a filter, and the filter is ultimately some kind of a electrical circuit with an op amp. So, you'd have some thing, just you could draw anything, whatever it might be. They often do this type of a thing, actually, a boosted notch, as it happens. I've run out of space to do the other half. People in electronics will know what I mean. You have the resistors there. It's all overlapped. They have some kind of a electronic filter, and that's what Bose have, basically. They have a few other tricks too, but ultimately the feedback filter is this electrical circuit that has different output at different frequencies, and you can create that the function that you want with it.
So then if that's the so-called hybrid or whatever we want to call it, so then this new concept, I guess, in the roadmap of this technology is what they call adaptive. So I guess the ANC1, ANC2 settings of some brands might be just the level of cancellation that they have. But with hybrid, I think they're looking at like the ability to not occlude certain frequencies. So like one of the functions would be if somebody talks to you, it would create a bypass for those frequency ranges. Is that what you understand adaptive to be at this point?
Slightly different concept. So I don't know adaptive very well, but enough to say in that feed forward diagram, the response of the speaker, the sound that you get out is very much dependent on how well sealed it is on the air. So if you have leakage, your low frequency drops off a lot. If you're familiar with that, if you break the ear pad on a headphone, all the low frequency is gone. It requires a strong seal,
right,
to get the low frequency. So if you had designed your filter for a situation where it's perfectly sealed, and the speaker has a certain response, and you draw some kind of diagram, like whatever it is, and then you break the seal, and all that low frequency is spilling out the gap and not getting to your ear, kind of a thing. The filter that you computed is now totally wrong, because that speaker response has changed by quite a lot. So an adaptive filter is you're trying to compensate for those changes by changing the filter.
Okay. I
think it's mostly for a feed-forward system. You don't do that. Well, you could do it for feedback too, I guess, but it's mostly for a feed-forward system, and it's trying to compensate for those changes, probably mostly in terms of sealing into the head, which have a huge impact on feed-forward.
Okay.
Now, how you actually do that, I'm not entirely sure. I think you have a feedback microphone, which you also use a measurement microphone to kind of sense that speaker response on the fly.
Okay. Right. Got it. Okay.
As well as a feed-forward microphone. I don't think you can do it without an internal microphone. I think there's no way to know what you should be changing to unless you've got an internal microphone for adaptive.
Okay, so I guess the adaptive part is just the tuning of the ANC depending on what that mic is picking up. I mean, open it up to free air, it's a totally different thing than if it's a sealed cup. Yeah.
So the original ANC headphones all used an analog electronic circuit to create the filter. Now it's mostly all digital filters. And I want to
Right.
mention something. I know that when you talk to people, especially in sales, that would be you, Dave, and they say, this chipset, Bluetooth chipset, has ANC in it, and our algorithm is better than our competition. It's total nonsense. They're all using exactly the same thing to calculate a filter.
Right.
It's not really an algorithm. You can call it, and of course you can call it an algorithm, but it's just a filter to create whatever function you're trying to get out of it.
Right. It's just a formula.
Yeah. And then a digital filter can do some things a little differently than an analog filter can, but not necessarily hugely significant. It's really the attraction to the digital filter is that you don't have to physically solder components onto a board to test things out. It makes that actually implementing it very easy.
So is that like the new AMS chip will have like digital filter inside the chip? Is that what we're understanding? And where the analog chips would have external filter components that need to be built into a circuit.
Yeah, exactly.
So that creates a whole bunch of other problems with noise and getting it right for production.
So in that comparison, thought about this a bit. The analog filter, you definitely need more board space because you just have to have resistors and capacitors to create your filter outside of the chip.
So we're probably in earbuds, we're probably seeing almost exclusively digital ANC.
Exclusively, yeah.
Okay.
There is a product, I'm not sure if Bose still do it. They did a feed-forward plus feedback earphones, noise cancelling headset. It might have been called like QC21 or something like that. But they had a big box externally with the battery and the electronics built into it. You ever come across that one?
No, but the Sennheisers, I think they were the CX910, something like that, and they had an external box with a couple AAA batteries. And I mean that was 2008, I think I bought those, so a while ago. But they got lost like everything else I own.
So in general, I think the digital filter does win just because of those advantages are so important. You don't need the additional board space, and it's a lot easier to develop with.
Any issues with power consumption with ANC headphones in general?
I think if a very well designed analog filter with resistors and capacitors would use quite a lot less power than a digital filter.
Right.
You have to be well designed so that the amount of current they're actually putting through the filter is very low. If you did it poorly, you could use a lot of power. But if you did it very, very well, you can use much less power on an analog because you just don't have to do any calculations and you have just a tiny amount of power going through the op amps and so on.
Right, and it's designed for a specific task, which, as we know, a lot of these ICs, they're using somebody else's silicon to run particular ANC process, so it's not optimized for that task. Yeah,
but having said that, of course, every year the power consumption of DSPs just goes down and down, so it's possibly at a level where it's not very significant.
Right.
Nah, it's still significant. It's still pretty significant, actually.
Okay.
So let's say you might have, for example, a fairly typical Bluetooth chip, just running Bluetooth without noise cancelling calculations going on. It's essentially what it is, just the computation of that CPU. You might be in the range of, say, 5 to 10 milliamps of current of power consumption to run the Bluetooth radios and decode A2DP data. Right. Then if you add in ANC hybrid, let's say, you probably add another 10 milliamps of power consumption for that computation. So it's still pretty significant, actually.
Yeah, especially for TWS without a lot of real estate for
TWS,
yeah. So, okay. All right. Well, I guess there's a shout out to the chip suppliers that do ANC. We want to talk to you guys next. So if you're watching, please hit us up, and we'd like to interview you, find out how you think your chip works and compares to or fits into this ANC ecosystem.
It's an interesting facet about that you just mentioned too, in terms of the chip suppliers and the timeline of things. So as you mentioned, Bose started work on ANC stuff, commercialized. They're the headliner. Others were doing it too, but they're the most well known. And, in the, whatever it is, 80s and 90s, they're starting to come out with products that are working with analog. But all this time, people, of course, knew the calculations and, in fact, had the ability to do DSPs, although power consumption was very high. You could do it with various computers. But it takes quite a long time to build up that tool set to actually make it realizable. And at the moment now, I see more and more of the Bluetooth vendors have really good user interface PC applications that let you just on the fly play around with these digital filters and test things out. Mm-hmm. And I guess the next step is you combine that with your measurement and automate that calculation of what that filter should be until finally you get to the point where you choose a chipset and a measurement. You just make a measurement and the chip is going to deliver the ANC that you want. For the moment, it still requires some engineer to fiddle around with the knobs and figure out what filter works and what doesn't, basically. But it's not far off becoming a very refined process.
Right, knowing the output and then having your inputs, and then it's back to this popular du jour, the machine learning, using kind of linear algebra type structures to calculate what these formulas need to be for each device in a blink of an eye, I guess is what you're getting at.
So I'm quite interested in that at the moment too, is how to so the digital filter is called a biquad filter. Usually that is the most common thing that is used, and you need to come up with these numbers called coefficients, and those coefficients determine what the filter does, basically, as a bump or a dip or high pass, low pass, and so on from these numbers. And what you want to do is come up with a target filter function that you want, and then have some way to calculate what all those coefficients should be. And so for the moment, if I do it, it's all manual. So I just have to sit down and swizzle the knobs until I get the curves to line up, basically. I don't know what is the calculation to do that, in the software. I just put in my curve and give me back the numbers. I don't know how you do that. I think it is a slightly difficult calculation to do because it's not that there's only one answer. There's an infinite number of answers to that.
Yeah, that's.
So how does the computer decide which answer is the right one? It's.
I think it's through having data sets. I would imagine, but I think we're getting a little over our heads in terms of like. It's. I mean, TensorFlow is kind of like the one, the software they use for this machine learning. And machine learning is just the ability to select multiple functions and determine which is the best function at that point in time. So it kind of sounds to me what you're pining towards is having that ability to pick the best function to get your solution in a blink of an eye.
Yeah. Some mathematician knows how to do this already.
Yeah, somebody that hasn't been inhaling Shenzhen fumes for the last 15 years.
Takes a while for these type of things to migrate into any particular industrial space, though. It's not overnight.
Yeah, for sure. I mean, they're trying to add machine learning to everything. So I know there's talk of adding machine learning to ANC processing. Like, what benefit can it offer in terms of adjusting to every atmosphere and every environment and having pass-through for people talking to you in an instant and recognizing...
Yeah, so pass-through, you just mentioned pass-through. Pass-through is essentially feed-forward in reverse. Right. So instead of cancelling the noise, you're going to compensate for the shielding effect of the headphone.
Right.
And drive a frequency response. So again, in principle, you could recreate the perfect sound as though you had no headphone on.
Right, using that would it use that mic on the outside to pick up?
You use the same mic, yeah. You just change the filter. All you do is change the filter that microphone signal passes through, so that when it arrives at the eardrum and mixes with whatever sound has come through the headphone, it sounds like exactly like you had no headphone on.
Right. Yeah. No, I have heard that some pass-through devices, people hear better. Like, of course, because it's amplifying what you're trying to listen to. So yeah, you would. And I think that technology is used a lot in hearing aids. They're trying to have this technology where you can focus and look at somebody, and it knows you're looking at them, and then it picks up in the kind of bar environment. You can hear that person better. That's. I mean, that's great technology. I think. some brands like Nuheara and Apple that are doing this quasi hearing assist function in their earbuds. I think that's a nice future, because straining to hear people in noisy environments is incredibly uncomfortable. So
definitely.
Okay, so I think that's a lot of good information to explain to people the difference between feed-forward feedback and I call it hybrid.
Hybrid's fine. I was going to say why I would prefer to see hybrid used for a feedback system that has a combination of digital and analog, rather than a combination of feed-forward and feedback.
Okay, interesting. Maybe we'll touch on that on a future date. So I guess everybody watching, thanks for tuning in to season 2. There's a lot more coming up. We got a huge backlog of guests that we've booked. So we hope everybody to keep subscribe, like, share, talk trash about us in the comments. We like that. So hope everybody enjoyed this, and have a great day. Thank you.
Thanks, Dave.